Okay, welcome back for our video on conservation of momentum. This might be either one or two videos depending on how fast this goes. And this is actually the end of the momentum unit, okay? Momentum is really important, but it actually doesn't take, because you've already done forces and kinematics, it doesn't take all that long to teach. Let's start off with a question. If it takes a net external force in order to change momentum, as we talked about in the last two videos, then what happens if there is no net external force? Kind of obvious. If a net force is necessary to change momentum, if there's no net force, momentum doesn't change. So there is no change in momentum. This is really important. Let's look at this example. Let's say we have two hockey players. They have different masses, and they are skating toward one another at different constant velocities, and they collide. When they collide, what has to be true about the force that hockey player A exerts on hockey player B and the force that B exerts on A? If you're thinking of Newton's third law, you're along the right path. Newton's third law says that those forces are equal in magnitude but opposite in direction. Well, if those forces are the same, okay, if the forces are the same, what can we say about the impulses that each exerts on the other? Well, we know that impulse is equal to the force multiplied by the time, the net force multiplied by the time. And think about it like this. You can't have one object exert a force for longer on the other object than that object exerts on it. So, in other words, A can't exert a force on B longer than B exerts on A. It has to be the same time. So, since the forces are exerted for equal times, the impulses are also equal in magnitude, opposite in direction. Okay? So the impulses, the changes in motion that they exert on each other, or that happen, are equal in magnitude and opposite in direction. And therefore, since impulse is a change in momentum, then we can just say that the changes in momentum are equal and opposite. Sometimes this gets misconstrued. Sometimes people think that this means that there's no change in momentum for either player. And that's not true. So it doesn't mean no change for each object. It doesn't mean that neither of the objects changes its momentum. Instead, what it means is that each change is equal and opposite the other. Kind of like if you have like two numbers, like let's say positive 20 and negative 20. Those two numbers, the magnitudes are equal, but the directions are opposite. So you can think of it like this. In a collision like this, what one player loses in momentum is gained by the other player. Okay? If this is true, if one player loses, but the other player gains the same amount, then the overall change in momentum for the two players is zero. So I'm not saying the momentum of each player stays the same, but if one gains some momentum and the other loses the same amount, the net change, if for both players, for the system, is zero, as long as there is no net external force during the collision. So as long as there's no external net force, as long as they're not like, I don't know, there's not like a giant gust of wind pushing both of them. Whatever the sum of the player's momentum was before the collision, it has remained the same after the collision. Some momentum was transferred between the players, but the total remained the same. This idea is known as the law of conservation of momentum. This is the first conservation law that you are being exposed to. Conservation laws are really, really important. Okay? Here's another way to say that. If F net, if the net external force is 0 newtons, then the total momentum of a system does not change during what I'll call an interaction. And what we really mean by interaction, the two main types of interactions that we're going to look at this year are collision or explosions. If the net force is 0, then the total momentum of a system does not change during an interaction, okay, some sort of collision or explosion. We can also represent this as an equation, just like most of the things that we've done this year. It's kind of silly to see it on the reference tables, but it's given right here, right under momentum equals mass times velocity. P before, momentum before equals momentum after. And I have no idea why they're using the words before and after, because we know what before and we have other symbols to represent before and after. Why don't we just call it initial and final? So you can do this if you want. This is what's on the reference tables, but I'm going to give you permission. Okay, if you don't want to write P before equals P after every single time, I give you permission to just write this, Pi equals Pf. This is the statement that the momentum of the system is conserved. Okay? Momentum might transfer inside the system from one object to the next if they're colliding, but the total momentum is going to be conserved. Okay? This is incredibly powerful. It's, like I said, it's the first conservation law that we're seeing. You're going to see 2 or 3 or 4 more. Okay, I can't remember exactly how many there are right now off the top of my head, but you're going to see more of this where we have this rule that shows that something is conserved, okay? Something doesn't change over the course of some event. Real quick, just have to point out these words before we really get going with the examples. There are 2 different types of collisions. Actually, I should really say there's 3, and you'll see why I'm saying that in just a second. The basic 2 are elastic and inelastic. Elastic, kind of like, you know how, like, you know, if you have like an elastic, something that's elastic, it's kind of stretchy, it snaps back to its original shape. That's not quite what we mean by elastic here. If we have an elastic collision, then you have 2 objects that must be interacting without losing any energy. And if you're like, what the heck is energy? Okay, well, everyone kind of knows what energy is, but it's really hard to define. We're not going to define energy until our next unit, but just you should know that an elastic collision means no energy is lost. Objects interact without losing energy. This kind of also means they do not stick together. Okay? In a perfectly inelastic collision, that involves 2 objects interacting and then sticking together. So the reason I said that it's really, there's 3 different types of collisions, is that you can also have partially elastic collisions, or you could call it partially inelastic, I guess it doesn't really matter, but just some sort of like, you know, it's not exactly elastic, it's not exactly inelastic. So for example, inelastic, that's when 2 objects collide and they stick together. Think of like if you're catching a baseball and it just goes into the mitt, that's an inelastic collision. The mitt and the glove are now stuck together, or they're touching each other. An elastic collision might be, for example, like a bouncy ball bouncing off the floor and then returning to its same height. No energy was lost. A partially inelastic or elastic collision means that the objects separate. They do bounce off each other, but not all of the energy was conserved. So think of, like, for instance, maybe if you're doing bumper cars and you collide with someone. It's probably not a perfectly elastic collision, but you're probably also not going to stick right together. So we're going to call that a partially elastic collision. We're mainly going to deal with purely perfectly elastic and perfectly inelastic collisions, though. But those are just some words that you should know. Inelastic and elastic. Inelastic means maximum energy loss. They're sticking together. Perfectly elastic means no energy is lost. Let's do the steps for solving a problem involving conservation of momentum. Here's our example. We're going to have like 4 steps here, so make sure you leave yourself some room to write. 2 carts move toward one another at constant speed across level ground. Cart 1 has a mass of 30 kilograms and is moving at 3 meters per second to the east. Cart 2 has a mass of 50 kilograms and is stationary. The carts collide elastically, and afterward, cart 1 moves west with a velocity of 0.75 meters per second. Find the velocity of cart 2. There's 3 steps. If you think that you might be able to use conservation of momentum in a problem, there are 3 steps that you should follow. So I'm going to write down the step on the left-hand side, and I'm going to perform it on the right-hand side. So we're going to split our paper like this. Step number 1 is to determine if F net equals 0 newtons. If yes, then momentum is conserved. Which means it doesn't change. The total momentum doesn't change. Okay? Individually, one cart might lose momentum, the other cart might gain momentum. Okay, so we have to check. We actually have to check this every time. Is there a net force on our system? We have 2 carts. It's level ground. It doesn't say anything about friction. It's level ground, so they're not getting pulled down by gravity. It doesn't say anything about anyone pushing the carts. So we are pretty free to assume right here that there's no outside force on this system. The system is just a collection of objects. It's defined as our 2 carts, and I guess the ground that they're traveling on. Okay, the net force on our system is 0. Now the 2 carts are going to push on each other when they collide. But that's an internal force. That's internal to our system because we said that our system is those 2 objects. We're looking at both of those objects right now. If they put forces on each other, that's internal to the system. So there's no external forces arising from outside of our system. So if that's the case, if there's no net force, then we say that momentum is conserved, and we write the following: Pi equals Pf. Yes, you should write this. It's kind of silly looking. The initial momentum equals the final momentum. It's kind of like saying, well, 7 equals 7, but it's a good starting spot. Step 2, for Pi and Pf, so both for before the interaction, in this case a collision, and after the collision, determine how many objects are interacting and write expressions for the momentum for each. So, before in this collision, we have 2 carts that are moving toward one another. Well, actually, one cart's moving, the other is stationary. Cart 1 is moving to the east. Cart 2 is stationary. Those are 2 separate objects, okay? So we have Pi and Pf. Initially, there's 2 objects. So here's what I'm going to do. I'm going to expand this. I'm going to expand the left-hand side into looking like this. P1i plus P2i. The 1 and the 2 just represent the 2 objects that I'm dealing with, okay? Otherwise, we would have had to figure out the momentum. I mean, this just makes it a little bit easier for us to see what we're talking about here. We know that momentum is conserved, and we know that there are 2 objects, so we might as well write out a term for the momentum of each individual object. Now, afterwards, we know that they collide elastically, which means they don't stick together, so we still have 2 objects at the end. So we have 2 objects before and after. So I'm going to do the same thing on the right-hand side. I'm going to write P1F plus P2F. All this says is that the initial momentum of the first cart plus the initial momentum of the second cart equals the final momentum of the first cart plus the final momentum of the second cart. And we know that to be true because, again, we got it from here. We said that the momentum was conserved. The initial momentum of the system equals the final momentum of the system. Now we're just breaking down our system into each individual object. But here's the issue. I'm not told what the momentum is at any point in this question. I'm given a bunch of masses and velocities, but I'm never told what the momentum is. So usually, you don't have to. Okay, sometimes maybe you are given the momentum like this, but usually we have to go a step further. The initial momentum of cart 1 must be given by the mass of cart 1 times the initial velocity of cart 1. I would write that like this. M1 V1I. The mass of cart 1 times the initial velocity of cart 1 must equal the initial momentum of cart 1. I can do that for every single one of these terms. Now, you might be looking at this and saying, why did we just make this so complicated? I would argue that this is actually simplifying things. Yeah, you have more stuff to plug in, but what the heck were you going to do with this in the first place? You were probably just going to look at that and be like, I don't know what to do. What we've done is we've written out this equation. We've expanded it out so that we know what to plug in. Okay, that's all we've done. If you're confused about the subscripts, you already know what I and F mean. You know it means initial and final. And you know that 1 and 2, well, that's object 1 and object 2. We have cart 1 and cart 2. Okay? So don't get freaked out just by looking at this. Don't think, oh, there's too many letters going on all over the place. I don't know what to do. Take the time to learn what these things mean. You already know what mass and velocity are. You know what I and F stand for, initial and final. And again, we have cart 1 and cart 2. So it makes sense that we label these things mass 1, mass 2, velocity 1, velocity 2. Okay? Get used to looking at stuff like this, okay? All we're doing, we're going through a process to make it easier for us to plug stuff in. That's the end of step 2. Step 3 is to pick a positive direction write the velocities accordingly and solve. So we need to pick a positive direction. Remember, in the problem, it said something about initially the cart 1 was moving east. Afterwards, cart 1 is going to be moving west. We need a positive direction here. Let's just make east positive. You could let west be positive if you want. You're going to get the same answer. Okay, so if we're going to let east be positive, then M1 is the mass of cart 1. Okay, that's 30 kilograms. The initial velocity of cart 1 is 30 meters per second east, so that's 3 meters per second. Positive sign. Notice that cart 2, even though it has a mass of 50 kilograms, initially it's stationary. So you know what I'm going to do here? Because V2I is 0, that whole term is 0. So we're going to get rid of it. M1, well, wait, we already know that. That's 30 kilograms. The final velocity of cart 1, it says it's moving west with a velocity of 0.75 meters per second. So 0.75, but I need a minus sign in front of that. Because it's moving to the west, I said east was positive, west must be negative. Plus 50 kilograms, and we're looking for the final velocity of cart 2. We already know the initial velocity is 0. We're looking for the final velocity. We still have a lot of stuff to calculate, but this is, there's one variable that we have to solve for. So let's get to it. 30 times 3 is 90. 30 times negative 0.75 is negative 22.5 plus 50 V2F. I'm going to add the 22.5 to the other side. I get 112.5 equals 50 V2F, and I divide both sides by 50. So I end up with 2.25 meters per second equals V2F. The final speed of cart 2 is 2.25 meters per second. And notice that that turned out to be positive. That must mean it's moving to the east. So it kind of makes sense. Cart 1 came in from the east, bounced off going to the west. Now we have cart 2 moving to the east. Momentum was conserved. You could go back and plug all this in and see if the left-hand side of this equation equals the right-hand side, and it absolutely will. That's conservation of momentum. Okay? It's a little bit of setup work, but then the math itself is not that bad. All right? We do have to expand it out. That can be a little tricky, but it's not too bad of a process. People usually catch on to this pretty quick. So I said there was only 3 steps. I do just want to make a note. And the note will go like this. If the masses stick together, and we know that they do that in what's called an inelastic collision. If you remember us talking about that. Then there's only one object on the final side. Okay? Because if the objects are stuck together, that means that they're moving at the same speed as each other. So we might as well just treat that like one object. So in this case, what we're going to do is we're going to add the masses together and use one velocity because they must be moving together. So if the objects had stuck together, let's figure out how fast they would have been moving at the end. It's the same situation. We're just saying the objects stick together. So we already know that momentum was conserved. Pi equals Pf. In the beginning, there were two separate objects. So I'm going to do, again, P1 initial plus P2 initial equals, but at the end, the objects are stuck together. So I'm just going to keep this as P final. Remember that we had, okay, so M1 V1I plus M2 V2I, but the second object wasn't moving initially, so I'm going to cross this off and write 0. Now the momentum at the end is a little tricky. Well, it's not tricky, but we're going to do something a little different. It's one object that's moving at the end, so there's only going to be one velocity, and the mass of that one object is just the mass of M1 and M2 combined. So I'm going to write that like this, M1 plus M2, and I'm just going to write V at the end. I'm not even going to put V final. I'm not going to put V1 and 2 final. I'm just going to write V because there's no other V over here to confuse it with. So notice that this has actually become pretty simple. 30 kilograms times 3 meters per second. We're going to assume east is positive once again. On the final side, the objects stuck together, so the total mass of the new object is 30 kilograms plus 50 kilograms, V. So I get 90 equals 30 plus 50 is 80, V. I divide both sides by 80, and I end up with 1.125 meters per second equals V. So we see if they stuck together, two would not have the same speed. Okay, it wouldn't have the same speed as before when they bounced off each other. Kind of makes sense. Okay, so those are two examples of very common conservation of momentum problems. In the next video, we're going to take a look at a whole bunch of other examples of this. Conservation of momentum usually ends up being something fairly straightforward for most people. They kind of like it, actually. That's all for this video. I'll be back for our last video in just a little bit.